Okay, here we are. Welcome once again to the Physics Video Lecture. Physics 105A Video Lecture 20. So we've been working on the driven oscillations, and we're going to, well, we'll do a quick review of that, and then we have one more topic in the driven oscillations. So I need some pens here. So here's what we had. We had the damped driven oscillation, and we had solved it, and we had looked at the amplitude curve. So let me reconstruct that whole thing. Damped driven oscillations. Our differential equation we're used to now. To F naught over M. So the right side is the driving force function of time, and we are now using the cosine of omega t. So our driving frequency is omega, and that can be dialed through the entire range of real numbers. This is the natural frequency of the undriven oscillation, actually of the undriven and undamped oscillation. So omega naught squared is just k divided by m from the original system. Then we found an homogeneous solution. So the solution to the problem where the right side is just equal to 0, we have discovered to be, we'll call it x sub h is equal to a sub h e to the minus gamma t cosine of root omega naught squared minus gamma squared t plus some phase. Okay. For the homogeneous equation, for the entire equation here, we saw that we could take this solution plus one particular solution of the inhomogeneous equation. This one is transient after all. It dies out as time, as time goes to infinity, this dies out. And so what we were left with was x of t. So after all that discussion, we had f naught over m. In fact, let's go ahead and write the amplitude in here while we can. We had the square root of omega squared minus omega naught squared, the quantity squared plus 4 gamma squared omega squared. So this was our amplitude that we spent some time discussing. And then we had cosine of omega t plus phi. So the response to this driving function is this phase shifted but same frequency. Okay. So the oscillator is being dragged along by the driving frequency, and for large times this goes to 0, and we're just left with this. And we had finally discussed the amplitude because we saw that, for example, when gamma is equal to 0, we get a divergence here at the resonant frequency. We had studied that as well. So the last thing we ended with was the analysis of this amplitude here. And I'll just very briefly sketch that. So amplitude resonance, that's a T. Resonance. So this we talked about. Let's just do the little graph there again. I'll say amplitude is a function of omega and it goes up and decays, right? And your resonant frequency is right around omega naught. Not exactly. You saw I had an expression there for the peak is just shy of omega naught. But good enough. Now here's the thing. Some oscillating system may have an amplitude and amplitude resonance, but you can't actually put a ruler up against it and measure it. Okay? On the other hand, an oscillating system may couple with something else. For example, it'll oscillate and make a sound, and then the sound is what you actually hear. And that intensity of the sound will be proportional to the energy. So what we want to go to next is what's called energy resonance, because that's the practical measurement that you can do from any systems. So next, energy resonance. So the energy resonance is going to, so instead of the amplitude, we're going to construct and calculate the energy. We're going to get something similar to this, but actually easier to analyze. Good, so we need the energy of this oscillating system here, this driven system. And this again is just the amplitude. So let's go ahead and calculate the energy of our driven oscillator. Well, the definition is just the kinetic energy plus the potential energy. Okay. So we have 1/2 m x dot squared plus 1/2 k x squared. And I should mention it right now. If you're talking about this k, right, you can say m omega naught squared, but we cannot say that's m omega squared. Those are two different things. Okay, just to bring our attention to that. So here is our x dot squared. We're just going to say we have equals 1/2 m, and then this is a cos omega t plus phi, so we have a, well, let's go ahead, x of t equals a cos omega t plus phi, x dot of t is equal to minus omega a sine omega t plus phi. So that's what we're filling in right here. So we have 1/2 m x dot squared, so we have omega squared a squared sine squared omega t plus phi plus 1/2 k, and then we're going to square this x, a squared cosine squared omega t plus phi. Now, in the undriven oscillator without damping, we had something very similar here, but then we could say that m omega squared is equal to k. That's not the case here anymore, okay? So then we could say m omega squared is equal to k. We factored out sine squared plus cosine squared equals 1, and then we said energy equals constant. Here, not the case. Energy is not constant. So that has to be stressed. Note m omega squared is not equal to k because of what I just said. This is just the driving frequency. So E is not constant. Okay. Just to drive the point home. So we have to do something else, but this is the energy. So for the moment, we have it. So there's the energy. It's not constant, but rather it is a function of time. But rather, energy is a function of time. So to make progress, we're going to do what's called taking the time average of the energy. And we had as a homework problem already to discuss the time average of these sine and cosine squared functions. So we can make use of those results. So we're going to take the time average. So next, let's calculate E, pointed brackets, which is the time average of the energy. So the time average of the energy, we have 1 over period 0 to period E of t dt. Okay. That's what we want to calculate. And to do that, we need the time average of sine squared and cosine squared. Period. But integral, so 1 over period 0 to t sine squared omega t plus phi equals the same thing for the cosine squared. dt. They both equal 1/2. So that was a homework problem. There's a way to see it very easily. You don't have to go to your integral tables. If you sum these two together, instead of taking them individually, if you add them, you're adding sine squared plus cosine squared, which is equal to 1. Okay. And you're adding a 1 then from basically from 0 to t, 1 over t. So each one of these individually is going to be 1/2. Okay. So we can make use of that, and now we'll go into here and construct our E time average. So now what do we have? We have a 1/2 in front of all of these things. So 1/4 and a squared, and then m omega squared plus k and now we have to go ahead and put the amplitude squared in that we have there before. So 1/4, let's go find that amplitude squared here. So we got the 1/4, we've got the f0 over m squared, I'll put that there in that form. And then what do we have, the m? We've got this m right here, and I'll factor that out. We'll have omega squared plus omega naught squared. Because if I factor out an m, then I have m omega naught squared is equal to k. So plus omega naught squared. And then in the denominator, I have, took care of that, yeah. Omega naught squared minus omega squared, the quantity squared plus 4 gamma squared omega squared. So there's our grand result, and it looks a little complicated. Make sure I got it all down right there. Yes? Put a square bracket here. Yeah, there's our result. And we're going to analyze, we're going to simplify it. Okay? This is not the one we want to analyze. However, just to have a look at it, you can see that, remember, omega is the driving frequency. Omega naught's the natural frequency. You can see that this thing's going to be to the fourth power. The denominator is going to be to the second power numerator. So 1 over omega squared, it's going to go to, I'll do a little picture right here. So this is the preliminary picture. So the energy versus omega will clearly have some kind of behavior like before, like that one up there. But we're going to simplify this. Okay. We have to simplify it because that's just too complicated. The simplification is going to be for the case where the gamma is very small. So the gamma is much smaller than the omega naught, which means to say it's a very slightly damped oscillator. We know that in the case where gamma is 0, we would have a resonance catastrophe, a divergence. So when gamma is small, we're going to have a very sharply peaked function. Okay? Instead of being broad, it'll be sharply peaked. So let's go ahead and take care of that. Okay. So now we'll consider the case where gamma squared is much less than omega naught squared. So the simplifications that are then possible are the following. Period. Near omega, so for omega close to omega naught, okay, let's write that clearly. For omega close to omega naught, right? We know the thing's going to be sharply peaked, so we can do that. For omega close to omega naught, we're going to go ahead and let omega squared plus omega naught squared be approximately equal to 2 omega naught squared, and this omega naught squared minus omega squared squared is going to be, that's supposed to be a 2 right there, okay, is going to be, this is an interesting one. So omega naught squared minus omega squared, remember that would be omega naught minus omega times omega naught plus omega. And if we're going to square that, that's what we'd have here. But now we're going to make use of this same expression here. Or not the same expression, but close to it. We're going to make use of omega close to omega naught. So that is going to be, this was still an equality. This is going to be approximately equal to omega naught minus omega squared times this 2 omega naught, the quantity squared. Okay. So that's the substitution that's going to deliver. And let's see what we get. Now, our time averaged energy of our oscillator, we've got quarter, we've got F naught over M squared. We've got M. We have 2 omega naught squared. 2 omega naught squared. We have 4 omega naught squared. From here, we have omega minus omega naught squared. The order doesn't matter because it's squared. Plus we have 4 omega naught squared gamma squared. So I also made the simplification here, okay? It's really this thing that's going to dominate the behavior. So the 4 gamma squared omega squared is replaced with 4 omega naught squared gamma squared. And now we have a lot of things that are going to cancel. See what we have here. We have an m's going to go away against that one. We're going to have 2 omega naught squared and these 4 omega naught squareds. Okay, that's good. So we're going to end up with another half. So we're going to have 1/8. We're going to have f naught squared over 1 power of m. And then we have 1 divided by omega minus omega naught squared plus gamma squared. Okay, so that's a significant simplification. We'll write it down again. This is called the Lorentzian. It's a resonance curve. So let's go ahead and just write it down on its own and discuss it a little bit. So again, this is the case where gamma was small, okay, so that this term dominates here. Gamma was small, and what this is really showing is the behavior near the resonance. Okay, so let's go ahead and do a graph, but this we can write down. We have f naught squared divided by 8m, and then we have 1 divided by omega minus omega naught squared plus gamma squared. So this one should be very easy to understand. There's E of omega, go out here to omega naught, and gamma's small, so it's just going to dominate here. And you know, we have something going like that, more or less. So the significance of this is the following. I have to go back to our driven oscillating system and imagine we're dialing up omega. We're starting very slow, very low frequencies, and we're dialing it up, and the energy, you know, ramps up and increases, and then as we keep moving higher and higher frequencies, we're going back down this way. So this we could think of as we could make it a little more beautiful, as an experimentally obtained curve here. Okay. That'll do the trick. So yeah, we're just changing the frequency continuously, taking our data. And so what can we learn? So when we take these data, we can discover what is the resonant frequency, and there's a little bit more. We'll have the maximum amplitude at the resonant frequency, And then we can also go down to 1/2. So this is E maximum. We can go down to 1/2 of E maximum, okay? And ask, how wide is this thing? Okay. So the height of the curve, the location of its maximum, the width of the curve. Those are things we can obtain from having taken these data, if that's what we're doing. And what do we see here? We have the max is just when omega is equal to omega naught, so we've got a gamma squared here, so that's F naught over 8n gamma squared. Okay. Now what about at the halfway point? Okay. We can get that width in the following way. So 1/2 E max, comma, when omega minus omega naught squared equals gamma squared, because then we have 1 plus 1 is 2 gamma squared, okay? So when omega minus omega naught squared equals gamma squared, or omega minus omega naught equals plus minus gamma, which is to say omega equals omega naught plus minus gamma. So the width here is apparently 2 gamma. Okay. Width here equals 2 gamma. So you learned about your damping constant and your omega naught, right? Your resonant frequency. But your omega naught, of course, tells you about the force constant or the force law in your problem. Okay. So yeah, let's hold on to that. Put this in some form, some words here. So we'll summarize it in this way. Analysis of the resonance curve. VE. So analysis of the resonance curve gives us tells us omega 0, right? And of course, since that's root k over m, that's telling you something about the system, right? We're talking about oscillating systems that you can't hold a ruler up to, okay? So we're getting it one part removed here. So it's telling us that, and 2 gamma, which we remember was the friction constant divided by the mass. And remember these friction constants, remember the Stokes law friction constant, that can be an important object in its own right. Okay. Maybe I'll add a note here. If you take your, let me see the form I have this in. Actually, this form here, these two are referred to as the quality factor of a damped oscillator. You know, basically the smaller the damping, the higher the quality factor. So those are also obtained empirically from this curve. And there you have it. Let's consult the clock right now. Okay, so that ends our discussion of the damp-driven oscillator, but not entirely. I'm going to use this discussion to segue into a discussion of Fourier series. So let's see. I'll do it this way. So let's call this Trigonometric Expansions. I can motivate them this way. Here's some, and bring a bunch of these things together. So here's what we had. On the one hand, we did the undamped oscillator, f of t over m. We had a completely general solution to this. For any f of t you could think of, we had a scheme to find that. So we had this for any driving force. And we could have generalized that construction to the damped oscillator as well, but it was better to keep it simple, okay? Then we had this one here plus 2 gamma x dot plus omega naught squared x equals, I'm going to write f naught over m cosine omega t. So we solved the damped problem, there's a square. We solved this damped driven problem just for a single function, the cosine omega t. This was fully general. There's a relation between these two, namely, and it turns out you can construct any function, more or less, using trigonometric functions. So having solved this for this one function, we actually would be able to construct the solution to the general one. This is a linear combination. So that's our upcoming topic, is how to expand arbitrary functions in terms of trigonometric functions. So I'll put this here as next. Expanding, or how about this, before we say expanding, expressing an arbitrary function in terms of trigonometric functions. And it's not going to be quite arbitrary. An arbitrary periodic function in terms of trigonometric functions. So that's our next topic. And I'll just get it started today, and we'll dive into it more next time. So let's see. Well, actually, maybe I'll leave that right now. So I'll once more. That'll be fine for today. So that's where we're headed. Kind of based on where we've been, I will say a couple things here. Remember, we had complex functions and integrations and integrals in the solution to this. Go ahead and look at that solution again. So when we express arbitrary periodic functions in terms of trait functions, we're going to go straight to the exponential, the complex exponentials, and we will make contact again with what we had up here. So it's going to tie together very nicely. But we'll leave it at that. Next time we'll jump in with both feet. And see you later.